Thank you very much for inviting me here to talk. So we'll talk about topics which somehow intertwine with geometry and information, which is, of course, the information loss paradox in black holes. And I will present here a work in collaboration with Andrea Dazzi, Pixin Chen, and Yongxi Wu. And I will slightly mention something that we're preparing recently with Chris Fields, who is here. So let me start and go directly to the main point here and summarize a little bit what is the problem, so the vexata question. So work very late back in the days by Wheeler and other people pointed out that the area of the horizon of black hole always increase, and the no-error theorem. So basically, we can understand the black hole physics just in terms of three parameters, which are its mass, its total charge, and angular momentum. So in the 73s, we had some preliminary work by Bekenstein on black hole thermodynamics, which were then followed in 74 by the proposal finally by Hawking on black hole radiation. But it's only on 82 that Hawking arrived with these ideas on interpreting entanglement entropy and deriving in this way an area law dependence. This has been done so far for entanglement in between matter systems along a boundary which divide a manifold into sub-manifolds. Then it's in 86 that Gabriele Veneziano, and then after the same idea was again worked out by Coleman, Preskin, and Wilczek in 92, arrived to the idea that we can actually introduce quantum errors in black holes. So, and this allowed for a slight change in the paradigm concerning the information loss problem for black hole. So, later again in 93 and 95, Toft and then in various work and then Saskin introduced the holographic principle, which is very much intertwined here with this information loss paradox. And somehow following this line of thought, coming back more closely to our days, in 2013, Saskin and Maldacena arrived with this idea of dr equal EPR, which is this proposal in which basically Einstein-Rosen bridges are taken into account as a possible primordial black hole, anti-black hole pairs which are maximally entangled. And this maximum entanglement should be a way to solve the information paradox. So what actually was happening that I didn't mention here is that 1 year before, Marolf, Polchinski, Almeri, and Sully worked out this firewall proposal. And in the firewall proposal, there was the idea that somehow the particle infalling the horizon of a black hole, which are entangled in going and outgoing particle, which are produced by the radiation, the Hawking radiation, their entanglement may break down, and this breakdown may produce a huge firewall. And this is contrary, of course, to the Einstein equivalence principle. Indeed, recently there have been also some phenomenological analysis saying that this could have been observed in LIGO, but of course, I mean, there's still a lot to be analyze better to understand if this is the case. But okay, well, anyway, so if this happen, of course, I mean, this is somehow an outrageous way of cutting one of the main principles that one can have in current physical theories. The problem here is that somehow the work by Pages and other that are very much accepted in the literature pointed out that these outgoing particles are entangled with the ingoing falling particles, but are also entangled with the past Hawking radiation. And this contradicts the monogamy principle of entanglement. And that's why these people arrived with this idea of the firewall. And then Sasky and Baldacina tried to question about something different, which was this ER equal EPR idea. Until, again, Hawking came back to the problem after listening some lesson by Strominger on the BMS symmetry, and proposed a different resolution of the paradox, saying that actually what happened is that the infalling matter, okay, which actually let enter some classical bit inside the horizon, is able to excite, sort of throw to some super translation to create some hologram, which is super translated by these symmetries. And this happens in particular space-time solutions, which are this solution provided with these BMS symmetries asymptotically. So, I mean, I will come back later on this, but I mean, they use this BMS symmetry argument then to claim this could work as a resolution of the black hole information paradox. So I will argue later, actually I will argue now, that there is some point here that, I mean, it must be indeed underlined. So this is, of course, is an infinite dimensional algebra of hidden symmetries, which is recovered in a soft infrared limit in this scattering amplitude. And this has been underlined by Strominger in previous results. The Strominger was, of course, coming from a quantum field theory perspective to this. So these are global symmetries of these null asymptotic space-times. So this BMS the BMS symmetry actually were studied first by Bondi, while he was studying indeed this null asymptotic space-time for purposes of defining gravitational waves on them. So it was because of this reason that they were studied. So then, I mean, it's, as I was mentioning to you before, I mean, Hawking wrote this short note proposing this idea in late 15, and then they came out soon with this paper. So here you can see, actually you cannot see, but you can more or less see something of this Penrose diagram in which you have an infalling null shells of a collapsing matter here. Here you would see that there is a green line which go over some blue line, which is the formation of the horizon of a black hole. Okay, and here there is the evaporation process. So there will be a line which separates these two regions here. And so what happens is that, I mean, it's you can define through this infinite dimensional symmetry some charges. So these charges basically what they do, they remove the degeneracy of the vacuum. So indeed it is one of the problems that eventually you may have why you consider this these symmetries, is that you don't even have anymore the conservation of the angular momentum, because this vacuum is full of soft photons, and these soft photons, of course, prevent from having a conservation of a quantity such as angular momentum. Actually, you have another problem which is bigger for these BMS symmetries, that they do not survive quantum corrections. So, which was some of the main criticism was derived recently. Actually, recently there have been some other criticism by Busso and Porrati, who underlined the fact that it's always possible to find some canonical transformation that decouple these soft photons, so these low energy modes from the other ones, so that basically they're not relevant for the resolution of the black hole information paradox. And there is also some other problem was underlined by Donnelly recently, which is in the fact that, I mean, it's what happened at region outside the horizon. Matter there should not be relevant for the information paradox. But let me go on to say that, well, here, I mean, as I said, basically, I mean, it's the statement by Donnelly Gidding was that software played no role then in this information paradox encoding. So, okay, but I mean, it's anyway, so it's okay, there is some problem in this BMS argument, but the whole idea is not totally to reject, in the sense that the new idea was that these infinite dimensional symmetries, which are not Lagrangian symmetries, may have some relevance. So then, I mean, it's a possibility is to come back to work that have been done in the past, in the 80s. So we're coming back to work by Veneziano, but also, I mean, Yongshu in particular, that has to do with the existence of solutions, okay, which are instantonic solutions for a Yang-Mills field on the four-dimensional space-time. So there is this work back to the 80s by Yongshu and other people that actually were able to find the existence of a Kac-Moody symmetries, so in three-dimensional algebra, which is related, connected to the existence of these instantonic solutions. So this can be actually linked to another factor, and here, I mean, I will introduce now two building blocks. Of course, I mean, so I will talk about instantons. I will try to review a little bit the idea of instantons, since no one of you could be eventually acquainted with it. It's very important. Instantons are everywhere in physics, especially in quantum field theory, and they are physical. They are extremely physical. So that, for instance, the U1 problem in QCD has been solved by a Toft thanks to the existence of instantons. So they seems to be things very theoretical, but actually they are real in the sense that they help. Other example of instantons which are famous in physics are sphalerons that interconvert leptons, leptogenesis into baryogenesis. So they're used in cosmology. So the other point that I will introduce, which is something proper of a model of semi-classical quantum gravity, is this space-time foam idea. So spin foam, for instance, which is one of the ways in which dynamics can be developed in loop quantum gravity in a covariant way, is an attempt to instantiate this idea of space-time foam. So this idea of space-time foam is actually an idea that was proposed back in the days, very back in the days, in the 50s, by Wheeler. So the idea is that space-time at a very short scale is not anymore smooth, but is somehow undergoing some huge quantum fluctuations, in which there is also fluctuations of topology, not only of curvature. And this is due to the fact that has, for instance, also Hawking notices and underlines in these papers the action of gravity is not conformally invariant, like, for instance, gauge theories are, Yang-Mills theory. So here, I will also proceed on two velocities, so to say, on two sides. So on one side, I will talk about this semi-classical analysis on scales, which I will call mesoscopic. If you want to quantify how microscopic they are, let's think to 10 to the 3 or more Planck scale, okay? And then we switch sometimes to an interpretation which is microscopic, microscopic, and then I will use intuition from low quantum gravity. So space-time form, as I was telling you before, is this idea which was proposed by Wheeler in '54, and in '78 Hawking was in some paper. Actually, I didn't put the other two authors, but I mean there's a series of papers with Page and Pope. Hawking was proposing that space-time form can be decomposed essentially in three main topologies. So, and these are SU2 cross SU2, K3, and CP2. So they refer to this SU2 cross SU2 as a virtual pair of black hole, anti-black hole, or if you want, white hole, from a quantum perspective. Although this SU2 cross SU2 is improperly is SU2 cross SU2, because actually in Euclidean quantum field theory, quantum gravity, let's say that what you're doing, I mean, let's say you're starting from S4, okay? So you're adding a point ascending to infinity. So this S4, you basically take 2 points and substitute the neighborhood with a Neguchi-Hanson and anti-Neguchi-Hanson metric, okay? And then take a point in the neighborhood of the two. So these are around 2 points which are, for instance, on the equator of SO4. And then send the point to infinity, and then you find the manifold, which is a topological SU2 cross SU2 minus P, which physicists call SU2 cross SU2, period. The metric on it is an Nerai metric. And this Nerai metric is, I will talk a little bit about that in a while, is a gravitational instanton. So it can be recovered as a gravitational instantonic solution. So let me introduce the other player here, which are instantons. And I mean, instantons, well, I mean, it's the first way to introduce instantons is to think, for instance, what happens in quantum mechanics. So in quantum mechanics, consider, for instance, 1 plus 1 dimensional space-time, and consider, for instance, just a particle, okay? And a very simple potential, double well potential. Of course, I mean, it's, you have the minima of these two. This potential, for instance, the minimum could be in 0. And you consider the path integral formulation of this. I mean, it's, you can also take into account a path that come back to the origin. So what you find is that you know that, I mean, you will find solutions which are tunneling in between the two minima, of course. And through the WKB approximation, you will find the amplitude of this tunnel. So, so instantons are giving another way to achieve the same results. So you can do this calculation, it's very easy, and what you can find is that instantons will intertwine between one minimum and the other, and of course they will give a blimp, because I mean a blimp in the this is the Lagrangian, okay? The tau is a parameter. Let's say that you can have an x of t, which is a trajectory which is going from one minimum to the other. And of course here the Lagrangian is minimum, but here is maximum, and then this is a blimp. That's why they're called instantons. They happen in an instant, instantaneously changing the value of the Lagrangian. So, and if you can compute this, of course, I mean, it's because this is the Euclidean theory, okay? You can compute this, and you can compute this through it's a Gaussian integral at the end of the day, and you will find that you will have a ground level with an imaginary component which is giving you exactly the same with amplitude that you would find with the WKB approximation. So these solutions are actually interconnecting different vacua. Okay. So now, I mean, here the thing is pretty much trivial. But think now at a little step forward is think at Yang-Mills solutions. I mean, Yang-Mills field in Euclidean space, and I mean you consider, for instance, SUN, okay, or SU2. Well, let's think about SU2 because later I will show just a particular solution. So for this one, the instantonic solutions are the one which are self-dual. So self-dual means that they are solutions of the self-dual constraint, and this is the way in which we define self-duality in Euclidean space-time. Okay? And the other thing is that for them, you can find that the action, okay, is always maximum that the action evaluated in the self-dual and anti-self-dual solutions, which is basically proportional, since this can be FF dual term can be written as the total derivative of the Chern-Simons action is proportional if the field configuration doesn't go too quickly to infinity, to some finite number, which is actually a relative number, and which introduces the third homotopy class of F3. So in this the relative numbers. So a particular solution is, for instance, the BPST solution for the case of SU2. So this is a solution which is interconnecting the value at infinity, so at spatial infinity, in this Euclidean manifold. And so, I mean, this is what we saw, for instance, before, for quantum mechanics, instantons interconnect different vacua. Okay, but the structure of the vacuum for Yang-Mills theory, of course, is non-trivial because of the redundancy which is introduced by gauge transformations. So this, of course, is particularly useful in physics, and for instance, you can introduce in this concern theta vacua, which solve the U1 problem and the strong CP problem. So this is the shift which is accounted from considering this term, and of course this introduces an effective action, and this effective action as a change in the path integral. There is also then this axial U1 symmetry problem. So axial U1 symmetry is not present in nature, of course, because we don't see double pairing of the pi meson. So it means that it's not present in the spectra of the particle in nature. So it must be somehow destroyed, and it is destroyed by quantum correction, and the only way to prove it is only if you have these instantons that does not allow the conservation of the axial current. So this is widely renowned in quantum field theory, in Yang-Mills theory. Is interesting in the fact that, I mean, it's quite recently, but following a line of thought that, if you want, is very much intertwined with low quantum gravity and with the very starting idea of the self-dual variable by Ashtegar in '86, was this notation by O, Park, and Young in 2011, which actually continue some old work by Samuel that was using the Ashtegar variable. So basically, you can do the same. You can recover these gravitational instantons also for gravity, okay, for gravitational configuration. And SU2 Ashtegar variables are exactly a way to do that. Okay, exactly the mean in which you can find this. Okay, so now let me come back to instantons again, and let's talk about instanton on space-time form. Okay, so now we have these three topological building blocks that we were considering before, but as Hawking, Page, and Pope tell us, these three topological building blocks in which we decompose the space-time form are such that only the SU2 cross SU2 contribution, which are the black hole, anti-black hole, or black hole, white hole virtual pair, is the dominant one. The other one are subdominant. So we can take into account this one, and we consider the Euclidean Array metric on it, and we reshuffle it in terms of complexified coordinates. And on this complexified coordinate, we notice that this decomposes into projective Euclidean Riemannian sphere, and on which you can find the Fubini metric. And basically, once you have this construction, you have exactly the same way to continue the analysis was performed during the 80s by Wu and other people to show that the existence of the Instanton solutions that can be recovered also allow to define some symmetries, which is a Kac-Moody symmetries. So we can find Kac-Moody symmetries on the C2S2S2 bubble, okay, in space-time form. And this, I mean, it's somehow passed through an ADHM similar-like formalism, but the fact that, I mean, in ADHM, d bar and dt translated here would be emission conjugate of each other, but this is not the case here. So it's interesting to notice first that this matrix here, which I call current, is shifting. It allows for a shift. I mean, it enters the definition of the field strength, okay, in these complexified coordinates, which, I mean, I will be back to it later. And when you now consider the transformation with respect to some parameters alpha and b and beta of this current, you find that they behave in this way. So basically, if you now define some generators with contracting on some functional derivative, okay, so this closes exactly a Kac-Moody algebra, okay, with central charge, which is the structure constant of the SUN that you were starting from. Okay, so basically, I mean, there is another hidden symmetries also in this space-time form decomposition. And this smells like the BMS, but it's different, of course, because BMS put the symmetries and asymptotic null spaces, while here, I mean, the symmetries is in the fabric, in the texture of space-time. So okay, so here, I mean, probably I could have talked about that earlier, but I mean, this is just to see how these gravitational instantons may arise also from the point of view of the quantum gravity. So you can see that, of course, you can define through the Ashtekar variable. So the first variable actually that Ashtekar was proposing were this self-dual and anti-self-dual variable, okay, which now would be accounted for as the restriction for the Mirzi parameter equal to plus minus I. A way to see it is, for instance, to consider the Einstein reduction reshuffled in terms of this two form here. This two form here is the Blebansky two form, which is the double wedge product of here. I will introduce a soldering one form, and then, I mean, the metric will be just a trace of this soldering one form. So F is the field strength of this self-dual connection, and through an ansatz that relate sigma to F, you can see that these solutions, well, I mean, you can vary, of course, with respect to the connection, and you will find again the Gauss constraint, so the covariant derivative of sigma to be 0. So basically, you have the Gauss, the Cartan structure equation. But I mean, it's the ansatz F equal lambda sigma allows you to solve the other equation of motion. And this is also telling you that in this context, the Blebansky two form is self-dual. This work, by the way, I should say this now, because on shell, in 4D, UDD, and of course, I mean, it's on shell, the internal Hodge dual and the external Hodge dual are proportional in this case. It's not, would not work otherwise in any dimensionality. So let me then continue on the way in which we can interconnect this macroscopic or mesoscopic, let's say, paradigm with the microscopic one. And here, I mean, it's I want to go to some results that we've been derived quite recently also by someone who is working here in Marseille, but I mean it's not here now because he's in Argentina for some visit. But I mean, which is Leandro Perez and with other collaborators of him. So basically, I mean, we can think at these two black hole, white hole, okay, and try to express them, since of course we have when we define this SU2 cross SU2, no, in Hawking ideas and so on, we define we use the construction through the Gucci-Henson, anti-Gucci-Henson metric, and which are by the way gravitational Instanton solutions. And I mean, so what we can do is now to think at this metric and to relate to them to the description in terms of isolated horizons. Isolated horizons are a null expanding horizon, so are basically horizon of black hole which have dimension 2 + 1 and topology of S2 cross R, you can see that, I mean, their definition entails an expansion rate which is vanishing, and the pullback of the energy momentum tensor contracted with the null vector on them is future oriented if the null vector is future oriented and is causal. So these are the properties that define this null expanding horizon. If on top of that there is an extra condition on the null vector, which is basically that the Lie derivative with respect to the null vector commute with the intrinsic derivative. So basically this entails the fact that the surface gravity on it is not evolving in time, it's constant. And so basically, I mean, this horizon can shake somehow, but I mean they maintain their surface gravity. On this isolated horizon, there have been shown some interesting things, very interesting, I would say. So I mean, eventually this guy were able to show that the two form, the symplectic two form on them can be decomposed. So it's now you can take into account, you know, this this isolated horizon, no, as a 2 + 1 dimensional manifold, okay, and you intersect them with the spacetime manifold, and you have this SU2 special slices, okay. So and you can decompose that, and you see that on the SU2 special slices, okay, you have a theory which is basically Chern-Simons. But it's not just Chern-Simons, but it's a Chern-Simons with some source, which is this sigma. This is basically the same Plebanski two form that we were considering before, that introduces what are called the punctures, because I mean this is the product of two triads, okay, because I mean we already imposed gauge condition, both the triads that acts like a grasping in the quantization, so like a left invariant algebraic derivative, as Simone was showing before. So, okay, so here it is. So basically, I mean, it's this pull out a matrix in this SU2 internal gauge context. Now this is this algebraic matrix. And it also can be discretized in terms of the punctures. So this is interesting for many reasons. It's interesting because it can be quantized through representations which are not representation of SU2, but are representation of quantum groups, which is SUQ2, which is the quantization of an enveloping algebra of SU2. And this object here is actually, if we consider root of unity representation, as a parameter which is a deformation parameter, this q. The deformation parameter usually is z, which is the logarithm of q. It is related to the q is the exponential of I, and is pi over k2, where k is the level of the Chern-Simons theory, and the level of Chern-Simons theory here is also related to the area of this isolated horizon. So basically, it's finite, the representation. So this is regularized. So this is the dimension of the Hilbert space here, and it's regularized. So also there is a regularization even on the entropy that you can define in this way. Of course, I mean, this is true for real variable, but here in whatever we have been discussing self-dual variable, because it's the only way in which you can define, of course, our instantonic solutions. So we have to do what has been done by Kac-Moody, Benachour, and the people at that time in Paris. Which is basically, I mean, this analytical prolongation continuation, which allows also to define this value of the area, which is in terms of real parameters, which is continuous, okay, and give rise to a level of the Chern-Simons action, which is also real and continuous. So it's somehow it's a different perspective. But what is important is that since we are taking into account a mesoscopic picture from the beginning, the area of this black hole, anti-black hole, must be finite a priori. So basically, I mean, the representation here is always finite, and also the dimension of the volume of the Hilbert space will be finite. So there is, I mean, there is a minimum area gap. And there is this relation here, the Chern-Simons level, okay, is expressed. So basically, it's proportional to the area of the S2 boundary of this isolated horizon. And so if we derive some nice consequences of that. So first of all, we have a finite dimension of the kinematical Hilbert space, which is due to the fact that we're using this representation, which is bounded by the level of the Chern-Simons theory. And the other thing is that the gradation instantons seems here to be supported on, are supported on semi-classical level on F3 manifold, okay, and then are Wick rotated. When we Wick rotate F3, we will have SU2 cross R. And this quantum level now are defined on this finite set of word lines, and they discretize this as a piecewise discretization of the domain, a piecewise linear discretization of the domain, of the continuous domain. That would be the description at the macroscopic level. So the other thing is that since we have been showing this before, okay, so it's you have that the field strength can be written in terms of the Chern-Simons, the Kac-Moody current, but the Kac-Moody current undergoes some Kac-Moody transformations. So it means there is a shift on the field strength for these self-dual variables, and this shift then, I mean, amounts to a shift also of the holonomy. So this Kac-Moody symmetry shifts also the holonomy. So this Kac-Moody symmetry is a symmetry is also at the level of the microscopic level for this Wilson holonomies, these loops, if you want. I mean, these Wilson holonomies then, I mean, introduce the loops in quantum gravity. So, and the other thing, of course, is that the Kac-Moody algebra here connect an infinite number of gravitational loops, okay, which are associated with the same punctures. In the same way, it connects an infinite number of instantons with the same center and shape, so but different charges. So this is the action of these Kac-Moody symmetries. So now, I mean, it's, let's see something always in this double picture somehow. So, and when we want to talk about the information encoding, it's peculiar the fact that the Kac-Moody algebra interconnects this infinite number of holonomies, okay, as I was mentioning before to you. But I mean, it's how this actually happened, okay, which is what now we're thinking with Chris more in detail. But I mean, so how this actually happened is through the action, okay, on the energy level of the quantum constituents, okay, of the matter fields that we have. So let me say also something about the fact that this Kac-Moody symmetries, okay, is a symmetry that you recover when you consider that your action, okay, at the path integral level, okay, is dominated by solutions which are the minimum solution, with the one that minimize your Euclidean path integral, okay, saddle point approximation, okay, are the minima if you consider the fact that instantons and anti-instantons do not interact each other. So basically, an instantons, if you consider now the quantum mechanical the quantum mechanical intuition of the double well, okay, potential, an instantons interconnect one minimum to the other, okay, anti-instantons goes in the other way, okay. So now, I mean, when you write your path integral, your Euclidean path integral, you sum over these solutions, assuming that they do not interact. So assuming that, I mean, it's these are high order, okay, corrections, and they do not affect your resolution of the path integral. But of course, I mean, this is true until you are in the dilute gas approximation. Once you're far away from that, because you have some interaction in between these instantons and anti-instantons, you have to put into account for these centers of these instanton and anti-instantons. You have to take into account some interaction Lagrangian. This interaction Lagrangian will, of course, spoil the duality and subduality condition, which are at the center of the definition of the Kac-Moody symmetries. And then, I mean, basically entail a dynamical breakdown of these Kac-Moody symmetries. So the information encoding is what must be refined in this picture. But I mean, I want to tell you what we have been thought so far, and which is the direction that, I mean, we're taking somehow. So here, I mean, we are thinking at this instantonic moduli has been associated to zero modes. So these zero modes are nothing but, I mean, Nambu-Goldstone bosons, okay, of these symmetries. But the symmetries can be spontaneously broken or dynamically broken, okay, by the instantonic solid in itself, because, I mean, they interact each other. And these interactions, generates a mass, which is a mass gap then, okay? And the value of this mass is actually a little bit difficult to evaluate, because, of course, you have to solve the path integral formulation. But I mean, it's what we know anyway is the order of magnitude of this mass gap. The order of magnitude is the order of magnitude of the energy scale that you have in your Yang-Mills theory. So if a level of energies, for instance, I mean, the series, I mean, the descendant scale, now you consider m equal 1 and, I mean, m equal 2 or m and m minus 1. The difference, which has to do with the excitation of the energy scale, the energy level that you can have in this scenario, okay, is proportional to the energy scale of your theory. So, for instance, for QCD, this would be 200 MeV. So, what does it mean? So, it means that that if you have your infalling object, suppose this is classical, that is in a certain superposition, so this will locally will entail to have some microconstituents, okay, which will excite this energy level and will imprint the Kac-Moody charges. And but then, I mean, the state, I mean, is encoded in this imprinting of information in these charges. Is not able, of course, to reproduce only a classical bit, but it produces only quantum bits. Okay, so it's you need some kind of decoherence happening in order to reform in a larger volume, in a voxel, how Chris Field would call, recreate a classical, let's say, bit. Okay. So anyway, so let me conclude. So that I was finished a little bit ahead, so that we keep back now to the. So there is this infinite number of different Yang-Mills and gravitational instantons, okay, which are interconnected by the Kac-Moody symmetries, all having their centers and shapes parameterized by some parameters and so on. So all with the same standard moduli, but different Kac-Moody charges, and the Kac-Moody symmetries interconnect them, and because it's changing the Kac-Moody charge. So we have seen that we can have bubbles that are topologically black hole, white hole, which are the ones that are dominant in the Path formulation in the space-time form approach, and that on them we can recover self-dual solutions, and we have developed a way to link this self-dual solution to some intuition that we derived, that we took from low quantum gravity at the microscopic as a theory, fundamental theory at microscopic level. So let me say that the infalling collapsing matter into black hole may excite the ground state instantons and of determined size and center into instantons with the same size and center, but they have different Kac-Moody charges, and this allows to have in this BMS picture, let's say, different than the BMS picture, allow to have information that is not stored anymore at the horizon, but is stored everywhere. That's the other point. So it's stored everywhere because it's everywhere you will find this texture, this fabric of space-time. So everywhere, even inside the black hole horizon, you can store information. There is also something that can be vaguely remember the ER equal APR conjecture, in the sense that there is this black hole, anti-black hole, or white hole, which are quantum constituents of this space-time form in this picture. Let's say interconnection, in the sense that they are really connected by these Wilson lines in this idea, in this picture that we consider, and somehow information flows from one to the other and backward. So somehow it's like it's bouncing, going forth and back in this microscopic picture. So this seems to be something that could be reminiscent of ER equal EPR. But the fact that ER equal EPR is assuming that, first of all, there must be some Einstein-Rosen solution which are classical and microscopic, and must be also stable. These actually, there have been some result recently showing that this conjecture is not universal, because there can be found example in which it fails, because there's the stability, of course, of wormholes is not guaranteed. So, and in particular, in some cases have been underlined, to show that ER equal APR, that cannot work at the classical level. But of course, it's here we're doing something at the quantum level, so we consider quantum fluctuations, because there are building blocks here. Okay, so I stopped torturing you, and thank you for your attention.
Is there any question?
I have two questions. The first is
in this framework, how we are thinking the expansion of the universe?
Well, the expansion of the universe is a classical statement. I mean, it can be classically understood. It's part of the classical solutions. So here we are considering microscopic and mesoscopic scales. So we are not touching the cosmological solution. So the cosmological solution will continue to be the same. So it will not be affected. So it's not affecting the...
And the second one is about the bubbles. There is a hierarchy of bubbles. You have some picture suggesting that you have a pyramid of bubbles.
No. The pyramid was just a zoom. That was just is a famous picture that you have in many popular science book. This is just is just a way to say that if you zoom, okay, you find this. If you zoom enough, you will find this this quantum fluctuation. It has nothing to. Thanks for the question. It has nothing to do with any hierarchy.
But there is a question: what happens between the scale of boson and
the scale of what?
Of the boson on the scale of the form?
So yeah, this question is a very important question for the whole fields, I think, of quantum gravity, but I think in general for the theory of quantum gravity. What happens in between the two? It's needless to say that we don't know yet. We don't have a theory who is able to, let's say, continuously answer what happened from the very microscopic scale to the large scale. But anyway, there is an understanding that we can develop in the sense that we know that going from the microscopic toward the macroscopic, there is some regime in which there are some emergent symmetry that appear. It's not only talking about the Kac-Moody symmetries, but I mean we may have also some hints about non-commutativity that can emerge. For instance, you may define also quantum operators in quantum gravity, for instance, that has to do with some position operator that you may define, okay, connected to length operators. And this may introduce some kind of non-commutativity, but this non-commutativity is effective only on a large spin limit. Okay, I mean it's not in the very very large one in which you don't find commutativity anymore, but in a middle step. Okay, and there is the middle step in which you may find, I mean theoretically, but eventually also experimentally, this is the hope, evidence of a Planckian or let's say quantum modification of space-time, which should reflect in a modification of the symmetry and then should reflect in a modification of the dispersion relation for a particle, for instance. Of course, this has not found so far. So it's so far is rejected by experiments, but we have control only on the first order correction in the Planck length. So we don't know if this can be true for second order and so on.
Okay, so maybe thank the speaker again.
Yeah, thank you.